This video discusses differentiations with respect to time. This includes higher order derivatives with respect to time. Usually, when you differentiate with respect to time, you do not go beyond the second derivative. So today we will see how to differentiate a given function of time with respect to time t up to the second derivative. Let's say the displacement of a vertically projected particle is given by s of t equals 10 times t minus 4.9 times t squared. This is actually the equation for a vertical upward motion under gravity, which was initially projected at a speed of 10 meters per second. This equation gives us the displacement. Let's say I would like to find the velocity. Velocity is equal to the first derivative of the displacement with respect to time. If I want to find the acceleration also, the acceleration is equal to the second derivative of the displacement with respect to time. If we have to evaluate the velocity and also the acceleration at a given point of time, let's say I would like to find these two quantities when t is equal to 1 second, I can substitute t equals 1 in the resulting equations of the velocity and the acceleration. So let's go ahead and first find the velocity of this moving particle. The velocity is given by d by dt st. I just have to look at the function st and differentiate it with respect to t. 10t when differentiated is going to be equal to just 10 minus 4.9 times t squared. The derivative of t squared is equal to 2 times t. Therefore, it becomes 9.8 t. That's the equation of the velocity. If I need to find the velocity at t equals 1, all I have to do is to substitute 1 in this equation. When I do so, I get velocity to be equal to 10 minus 9.8, which is equal to 0.2 meters per second. Next, we will find the acceleration. The acceleration is the second derivative of the displacement function with respect to t, which you should write as d squared st over dt squared. In order to find that, I need to differentiate the first derivative of the function of displacement. 10 differentiation is equal to 0. When you differentiate negative 9.8 times t, it just becomes a negative 9.8. Now, if I wanted the acceleration at t equals 1, we simply have to replace t equals 1 in the equation of the acceleration. The equation of acceleration doesn't have a t. Therefore, the acceleration in this case is a constant, and that acceleration is equal to negative 9.8. The units are going to be actually meters per square second. We will look at another example. In this case, I have a path of a moving particle on a 2D plane, and that path is given by two parametric equations of time for the x-coordinate and the y-coordinate respectively. Let's say the x-coordinates are given by the function x of t, which is equal to 5t to the fourth power minus 2t cubed plus 3t squared minus t plus 5. Let's say the y-coordinate at a time t is given by 4t raised to the third power plus 5t minus 3. Find the acceleration at time equals 1. The units are not given, therefore I don't know the units of the final answer. We will just go ahead and derive an equation for the acceleration. We know the acceleration is the second derivative with respect to time. Therefore, I will first find the first derivatives with respect to time. and those resulting functions can be differentiated again in order to find the accelerations. So if I differentiate the x ones with respect to time, it's going to be 20t raised to the third minus 6t squared plus 6t minus 1. If I differentiate yt one time, it's going to be dyt over dt equals 12t squared plus 5. Those two functions are the parametric functions of the velocity. In order to find the acceleration, I need to differentiate each of these two first derivatives one more time with respect to t. When I do so, I get d squared x t over dt squared to be equal to 60t squared minus 12t plus 6. When I differentiate y with respect to t one more time, we get d squared yt over dt squared. That gives us equal to 24t. Now, using these two equations, we can find the components of the acceleration along these two directions. So, acceleration along the x-axis should be equal to, we need to find the acceleration at t equals 1. Therefore, in order to find the acceleration along the x direction, we need to substitute t equals 1 in this equation. When we do that, we get 60 times 1 minus 12 times 1 plus 6, which is equal to 54. And then similarly, we can find the acceleration along the y-axis. In order to find that, I need to substitute t equals 1 in the equation right here. Then it becomes 24. If I also need to find the resultant acceleration, we may do so, because along the x-axis, the acceleration is 54. Along the y-axis, the acceleration is 24. How do you find the resultant acceleration? In order to find the resultant acceleration, we can complete this parallelogram, which actually is going to be a rectangle. The resultant acceleration should be given by the direction and the magnitude of its diagonal. You can find the length of this diagonal using the Pythagorean identity. If I write it as r, that resultant acceleration should have a magnitude of square root 54 squared plus 24 squared. You can simplify that. You can also find the angle. Let me say this angle is equal to theta. That angle theta should be equal to tangent inverse 24 over 54, which we can actually simplify and write it as tangent inverse 12 over 27. You may use your calculator and find the angle in degrees as well. That's a complete answer for that second example. That should end the discussion for this video. Thank you so much.